Okay. Also, I will keep this, slides, upload this slide, so you can later on download these also and read for your reference. So you don't need to copy this now in your notebook. You try to understand. And also, as far as textbook is concerned, you can follow any standard physical chemistry textbook. Okay, so these you will find in any physical chemistry textbook. One of the best books is Physical Chemistry by Atkins. Okay, in case you have it, it is fine. Otherwise, any standard physical chemistry book, if you have, then that should be fine. You will find these topics there. Okay. So basically, all these processes are happening everywhere, and there is an energy transformation associated with these processes. Okay. And thermodynamics is the subject which studies that in a quantitative manner. So that is why it is one of the most, you can say, the pillars of science. Okay, fundamental science is the thermodynamics. Okay, it is across any discipline. You will see even in science and engineering, everywhere, thermodynamics explains processes. Okay, why one process is happening, why another process is not happening. Okay, so all these questions thermodynamics can answer. Okay, so it is basically one of the fundamental science, and the only thing is that depending on the subject, you can have a different ways of explaining the properties, but basic principles remain the same. Okay, so that's why it's a very, very important topic, and it is based on few fundamental laws and concepts. Okay, thermodynamics is always based on some fundamental laws. Thermodynamics, first law, second law, third law, zeroth law. You are probably aware of several of the laws. Okay. Another few concepts that we need to clear when we talk about thermodynamics. One is the work. What is work, and how will you define the work has been done? Okay, who is doing the work? Whether work is done by the system or whether work is done on the system. Okay. So these are some different concepts. Sometimes the confusions arise, so one has to clearly understand what are these. This convention is very important in thermodynamics. So we define work. Okay. So we define work when an object is moved against an opposing force. Okay, this is the standard definition of work. If there is a force, and if you are moving, that means that the displacement against the force, then you say that there is some work done. Okay. So for example, if I carry a weight and if I go up gradually, if I change my position, then I am doing work. Okay. But if I carry a weight, if I don't move, then actually the definition, I am not doing any work. So that means that is why change in height of a weight. If you are carrying a weight and if there is a change in height, then that is a measure of work. Okay, so that's what we will see. Always work we will consider as a movement against the force applied on the object. Okay. Then these are the few concepts. You already know that entire universe we can divide into two parts. One is called the system and another one is called the surroundings. Okay, systems and surroundings. Which part is of the universe is system? It is a part of the universe which is chosen for the observation, where the process is happening. So that part is the system. Okay, suppose you are performing a chemical reaction in a container, in a beaker, in a laboratory. So that is your system. Okay, and what is your surrounding? It is basically the rest of the universe. Okay, theoretically rest of the universe, but most likely the immediate surrounding, region around the system, that we call is surrounding. That means if I perform the experiment in a laboratory, then that container is my system, and the room or the laboratory where I am performing is basically the surroundings. Okay, and these two together what makes an universe. Okay, systems are generally separated from the universe by very clear boundaries. Okay, very clear-cut boundaries are there which separate the system from the remaining of the universe. That means between system and surroundings. Okay. Now, depending on the nature of the system, there can be different types of systems we can consider. Okay. These most common, these are the three systems that we often deal with. One is known as the isolated system. You know, isolated system means when there is no exchange of energy or matter between the system and the surroundings. There is no exchange of anything, no exchange of energy, no exchange of matter. It's a completely, we call it a system is isolated. That means it is surrounded by some adiabatic walls. Okay, adiabatic walls means the walls which do not allow flow of energy or or heat across the boundary. They are known as the adiabatic wall, and of course they don't allow the passage of material or matter between the system and the surroundings. So they are called isolated systems. Okay, say for example, if we keep a liquid, whether hot or cold liquid in a thermoflask, then that is a closest example of an isolated system. Okay. But in reality, you cannot make 100% isolated system. So therefore, over the period of time, say after several hours, if you keep, then gradually we'll see that your the hot water will lose. It become gradually will become normal temperature, or if you have a cold liquid, if you have kept in the thermoflask, it will become warmer after a long period of time. But it will remain like that for a significant amount of time. So that's an example of isolated system that you can think of. Then another type of system is known as the closed system. Now, closed systems are those where the system allows energy to flow across the boundary. Now, energy can flow between system and the surrounding around the boundary. So that means the walls now allow energy to flow either from the system to surrounding or from surrounding to system, but there is no matter flow. Matter cannot be transferred. Okay, no matter can exchange between the system and surrounding. So these are the closed systems, and these closed systems are separated from the surrounding by what we call diathermal wall. Okay, they are diathermal wall. That means they will allow energy or heat to flow. Okay. So the typical example will be, say, if you keep a container, regular container, and if you keep a liquid, say hot liquid, if you keep in a cup or a glass, you feel hot the surface, because our inside temperature is very high and the surrounding is low temperature. So heat will flow from the high temperature body to the low temperature body. So therefore, after very soon, after some time, few minutes or few seconds, you will see that your temperature of the inside the container will go down and that of the surrounding will go up, and at some point of time there will be equilibrium. So your temperature of the container will become the same as that of the surrounding. This is the common thing that we see. Why that happens? Because this system, in your case a glass or a cup or some container, which has a wall which is diathermal in nature. So that wall allows heat to flow in depending on whose temperature is high and whose temperature is low. Depending on that, it will decide the direction, but it allows exchange of energy or heat across the boundary. So they are known as the closed systems. Okay. Then you have open systems. What is an open system? Open, the word open means it is open for everything. That means both energy and matter actually can transfer between the system and the surrounding. Such a system is known as an open system. Say, for example, liquid, if you keep a liquid in an open container, okay, you have seen, if you keep a liquid in an open container and then if you come back after some time, you will see that the volume of the liquid reduced, okay, will be reducing in that container. Okay, the reason is that from the surface, because it's open, there was no cover, so therefore some liquid will gradually evaporate from the surface. Okay, it will go to the surroundings. So because your system was open, so that means the amount of material or the matter present in the system will decrease. Okay, and somewhere it will increase. So there is an exchange between the system and the surroundings. Okay, and of course energy can be transferred. So there is another example also. Say, for example, the liquid separated by some porous kind of a membrane, okay, or some kind of a membrane which has a lot of pores, and through the pore you can allow the matter to flow across between one side to the other side of the membrane. Okay, so this is another example, and this is actually a way of you can separate liquid mixtures. Okay, if you have two liquids, suppose two liquids, immiscible liquids with different type of particle size, molecular atom size, then you can selectively allow one particular type to pass through the pores. You can design the pore in such a way, and in that way you can actually separate the two. You can purify the liquid. Okay, so these are used. This concept is used in various places, particularly in industry. So this is important, therefore, open systems where you allow both energy and matter to transfer. Okay. Now in thermodynamics, you have different laws. First law is probably the most fundamental law. Okay, and this is the common expression that we write. Delta U equal to Q plus W, which means that this is basically gives you it's a conservation law. Okay, energy conservation law. That is the first law. Okay, what it physically means is that if you have a system, if there is a heat exchange happen or energy exchange happen between the system and the surrounding, and system does some work. Okay, so these two will be contributing the change in internal energy of the system. Okay, so internal energy will be a sum of the energy exchange between the system and the work done during that process. Okay, so these two together will give you the change in the quantity which is known as the internal energy. What is internal energy? Internal energy is basically the total energy of the system. Okay, it is just a total energy. It is just the energy by virtue of the presence of the system. Okay, and that is, we call it the internal energy. It is the energy possessed by the system, which is nothing but a sum of kinetic and potential energy. Because if you take a system, it has many atoms or molecules present in it. So all the atoms and molecules, they are actually under motion all the time. So they have some kinetic energy. Okay. At the same time, they interact with each other. So there is some potential energy coming into the picture. So this sum of this kinetic and potential energy, that is the total energy of the system. That is what is known as the internal energy. Why it is internal? The term, because it is the internally possessed by the system. Okay. Now you can actually prove that such an energy, internal energy, exists by, say, for example, a liquid freezes into solids. Okay, you keep a liquid at a low temperature, say water. If you keep at a low temperature, then it can freeze into ice without doing anything, without supplying any energy, without taking out any energy. So that means that there must be something present within the system, okay, which allowed this process to happen. Okay, so that shows that the liquid, by virtue of its existence, must have possessed some kind of energy which it used to carry out that, in its change of its phase, say from liquid to solid phase or vice versa. Okay, so that shows that there is some energy that is system possessed due to its existence, and it is known as the internal energy of the system. Okay, and so this is the common, or you can also write it down in the differential form. Okay, this is the first law mathematical form. Now, what is internal energy? As I told you, now these are some of the very characteristic properties of the internal energy. Okay, this is it's an extensive property, because that means it depends on the matter, the amount of the matter. Okay, number of moles of the atom, the amount present. If you increase the mass, if you increase the amount of the material, then you will change, because it depends on the mass. It's a state function. Okay, state function means it's only characterized by the state, a particular state of the system. State is defined by, again, pressure, volume, and temperature, some independent thermodynamic parameters, pressure, temperature, or volume. Generally, these are independent parameters. Two of them can be independent. If two of them are independent, then the third one is automatically fixed depending on the equation of state. Okay, you have an equation of state. In the equation of state connects between pressure, volume, and temperature. Now, if you have any two of them, you can independently vary, and the third one will then be determined by the equation of state. Okay, so therefore, it's a state function means it depends on the state parameter only. Okay, its change is independent of the path. So no matter, suppose I have a two states, state I and state F, initial and final state. So what will be the internal energy of state I will depend on that particular state properties. Internal energy of state F will depend on its state variable values. That means pressure, volume, temperature, etc. And if I go from state I to state F, it doesn't matter which path I follow. It will be independent of that. So change in internal energy for going from state I to F will be simply the difference in internal energy of state F and that of state I. Okay, and state F and state I internal energy will be determined from the corresponding state variables. Okay, how state F is defined, that will tell you what will be its internal energy. How the state I is defined with respect to its pressure, volume, and temperature, that will tell you what is that corresponding internal energy. So this, since it depends only on these two states, it does not matter how you travel from I to F. So these are actually independent of path. Okay, the path independent function, state function. Therefore, we call it as a state function. And if you do a cyclic process, if I go from I to F and if I come back to I, okay, what will be the change in internal energy? It will be 0, because both initial and final states are the same now. Suppose I start from state I and come back to state I again, then both delta U will be UI minus UI. So it will be basically 0. Okay. So for any cyclic process, means if you come back to the origin, then the complete change in internal energy will be 0. There will be no change in internal energy. And this is a typical property. This is a typical property of any function which is depends on the state. Okay, or any variable which is a state function. Okay, it is independent. It is applicable to that. Not necessarily internal energy. We will see that this is applicable to all of the thermodynamic functions: enthalpy, entropy, Gibbs energy. All these things, they exactly satisfy the same conditions. Okay, so we can write down U, or this is in general any thermodynamic functions we can write down in terms of like this: function of any of the two, volume temperature or pressure temperature or pressure volume. Okay, any two of the three thermodynamic variables. Okay. Now, if U is a function like that, then we write the total change in internal energy can be written like that. You know that we can write it down in a partial derivatives form. Okay, where partial derivative means here when a function is a function of many variables now, a function of more than one variables, then the total change in the function for given changes of the two variables can be written like this. Okay, this is known as the in terms of partial derivatives. So what you do, you first change one of the parameters, keeping the other one constant, and see how the change happens with respect to that. Okay, and then multiply by the minimum, the small amount of change that is been made in that parameter, say volume. So this gives you the total change of U due to change in volume, keeping temperature constant. And then next time you do change the temperature, keeping the volume constant, and they multiply by the change in temperature, you will get the contribution arising due to change in temperature at constant volume. You sum up these two, you get the total change in internal energy. Okay. So this is the concept of partial derivative. I think you already know what is partial derivatives, but for clarity, I will quickly tell you what partial derivative is, and in general how you apply what are partial derivatives are very important properties. Okay. So as I already said, partial derivatives are used when you have a function which of more than one variables. If the function depends on only one variable, then you can write it directly full derivatives, that you know that. But when a function, you have a function which depends on more than one variable, say z equal to function of x and y. Okay, in such case we write the changes in terms of partial derivatives. Now if you say this is one partial derivative with respect to variable x when y is constant, this is the partial derivative with respect to y, x is constant. So what are these quantities? These quantities, if you say, it is basically slope of the function z with respect to x when y is constant. Okay. So partial derivative is basically the slope of the function with respect to one of the variables that you have taken, other one if you are keep constant. So if you plot how the function z changes when you change x at constant y and find out the slope, that will give you this term. Similarly, if you plot how the function z changes with y, find out the slope at constant y, that will give you this term. Okay. Now, so in terms of definition, you know that how the derivatives are written in terms of limits like this. So you can write it down that, you know, limit h tends to 0 if you have f function f you change by small amount, x plus h, y remains the same. So find out the differences of the function and divide by this h. So this is by definition is this derivative. Okay, derivative of z with respect to x at constant y. Similarly, you can write down like this. Okay, I am changing the y now at keeping x constant. So x remains constant, y changes, and then divide by k, limit k tends to 0. This is the definition of this term. Now, if both are changing now, x and y both are changing. Please mute your mic. Yes. Somebody saying something?
क्लास भी आ रहा है, तो पढ़ाई करनी पड़ती है, बताओ याना यार फीस जमा करने.
So what I will do, I will mute all of you, and then finally maybe.
तेरा वो तो लिख दे, अकाउंट नंबर लिख के व्हाट्सएप कर दे, इसे जमा करूंगा. जल्दी बता.
Okay, so this is the whole. Then this is the partial derivatives. Then what will be the total change in z? Will be simply this is the change per unit x, and then multiplied by the amount of change in the first variable y is. And similarly the other term, if you add these two, you become total derivative, total change in z. So this is what is the how you write the differential in terms of partial derivatives for any function of many variables. This dz is called the perfect differential. Now it has two important properties. This will require in thermodynamics. We use this very unique properties. These are mathematically can be shown is that if you take a second derivative of this function that is independent of the order of the changes made. That means independent of the order of the differentiation. The way you have carried out. That means if I carried out the first derivative with respect to y and then take the second derivative with x, or if I carry out the first derivative with x and then second one by y, it is independent of the order. The values will be the same. Okay. So the material, once you take the second derivative, which derivatives are taken in which order? No, the order of the two variables. So it is independent of that. There is a second one. Condition which is very important. This is known as the cyclic rule or the chain relation. If you do cyclically the derivatives and take a product, say del x del y at constant z into del y del z at constant x into del z del x at constant y. See, it is cyclically done. Zx zxy, that is equal to -1. Okay. This is known as the Euler chain reaction relation. So these two are fundamental properties of for any function of many variables in terms of the derivatives. Okay. Now you can take an example. Say for example, very simple things. Temperature we know it's a state function, so we can write it down in terms of function of pressure and volume. Say for example. Now let us take for its simplicity. Ideal gas PV equal to RT. Then if you take the derivative. First you take the derivative with respect to volume.
पैसे कैसे निकालते हैं बैंक से?
वही वाउचर लेना पड़ता है, उसमें लिख दो और फिर डिटेल वगैरह और सब
क्या डिटेल लिखाता है ऐसी?
तू नहीं खा सकता, तेरे तेरे खाता प्रेशर ही, तू चिंता मत कर। सारे इधर पूछ रहा है।
बता तो।
अरे जिसका खाता रहता है उसको फाइन लगते हैं बस, बाकी
अच्छा,
और फालतू लगेगी।
फिर तो ठीक है। कॉलेज चालू हो गए, पढ़ने चालू हो गए, पहले दिन यार आज तो।
If somebody is disturbing in the class, who is that?
और मैं दिख रहा हूँ।
Can somebody find out who is
भाई
talking?
ये क्या है?
I muted everybody.
लाइट आ रही है।
शायद मेरा माइक एंड म्यूट था। अकेले उड़े गया। तो भाई यार मैं पूछ लूं किसी से, भाई मेरा दिख रहा है चलता हुआ।
Priyank Srivastava, are you talking?
बोल रहा है, अरे साले, अरे
Okay, so if you take, say for example, the ideal gas equation and simply find out the first derivatives. Okay, say I took del T del V, I get P by R, del T del P, I get V by R, first derivative. Okay, so first with respect to V, then with respect to P. Now I take a second derivative. Here I take second time I take a derivative with respect to pressure. Here second time I take a derivative with respect to volume. Okay, now if you do that, then see both cases the result will be 1 by R. Okay, so the second derivative will be independent of the order. Same thing if you follow the cyclic derivative rule. Suppose I do the del P del T at constant V, I get some value, then I do del T del V, X, Y, Z, Y, Z, X, then Z, X, Y in that way, then you will get three values. Now, if you multiply this derivative, you will see that you will get -1. Okay, so this can be very easily shown. Okay, so that shows that if temperature is because of the state function, dt is a perfect differential. Okay, because it follows these conditions, so therefore it is known called the perfect differential. Okay, now this one I will skip, so you can simply take just a simple mathematical expression and then you can take a derivative and show that these things are valid. Okay, so this is simply z equal to two function of two parameters, two variables x and y. Okay, anyway, so now let us go to the partial derivatives. Will be using thermodynamics throughout, so that's why you should not have any confusion on that. Okay, now let us talk about work concept. What is the work concept? Which is required because we'll next onward we'll use this work everywhere. So we have to clear what is how to define the work and what convention will follow. And most of the cases will be dealing with mechanical work, that means expansion and compression of the system. Now this is a very common way of understanding thermodynamics. We take a very simple kind of a system. This is our system where you have a cylinder. We have a cylinder fitted with some kind of a piston, and the cylinder contains some gas. Okay, so depending on the pressure on the piston, this gas, this can be expanded the volume, or it can be, gases can be contracted depending on the pressure of the system. And this piston is frictionless, we assume, so that there is no work, loss of energy across the boundary and all. Okay. Now, what will be the work done? Suppose this is an external pressure I call PEX. Now, you move the piston in this direction by a small distance, say Z. Suppose this is Z direction, so you take dZ. Okay. So what will be the work done? Work is equal to force into displacement. So since the displacement is against the force, so the work done will be F into dZ minus of that. Okay, because direction of the displacement is different, is opposite to that of the direction of the force. So therefore, we give a there will be minus sign here. So force into displacement, this is the work done. Small amount of work done because we have moved by a small distance, dz. Okay. Now what is force? Force will be pressure into area. So therefore we can simply write, if this is the pressure applied on the piston, and suppose area of this one is A, so therefore it will be pressure into area this one, and A into dz. This is the area of this piston and this is the Z, dz. So they actually constitute this volume. Okay, the change in volume. So therefore this term becomes dV, the change in volume. So by this, if we now continue this process and until I reach a final volume, suppose initial volume was V1 and final volume was V2. Okay, once the process stops, the volume becomes V2. Then what will be the W? W will be simply work will be integration of this. We can simply integrate this between the initial value and the final value. Okay, so this is therefore is the general expression of work. Okay, minus PEX, external pressure, volume change. If we integrate between initial and final volume with a minus sign here, okay, this becomes the total work. Now different cases can arise. Now you can have different cases. Say for example, first one is that you have a free expansion. Okay. That means you are expanding the system against zero pressure. Okay. System is expanded in vacuum. That means now if the pressure is zero, of course, then the W will become zero. So that means there is no work done. Okay. System does not do any work if you suddenly make the pressure zero and volume changes suddenly, but there is no work done. Okay, because here pressure equal to zero. Second, possibility is that you are expanding the system against a constant pressure. I keep the final pressure very constant. Okay, all the time I'm keeping a constant pressure. I'm not changing the pressure. That is basically what we term as the irreversible process. Okay, there are two types of process. One is irreversible and one is reversible. Irreversible process is that when you have the external pressure is constant, and then against that constant pressure, you are changing the volume of the cylinder. Okay, so that is the process. So since pressure is constant now, so it comes out of the integration. So therefore, you have simply work done will be simply pressure into the volume change. Okay, so minus P external into the delta V, the volume change. So if this is the pressure versus volume, if you plot, if PEX is constant, then simply this will become work will be just the area of this part. Okay, that will be give you the work done. Now another way is that reversible expansion. What is reversible expansion? Reversible expansion means where changes occur in successive stages. Okay, what happens? Changes are occurring in successive stages with infinitesimal quantities. That means very small changes you are making. You are making a large number of such small changes, and so that you go to the final state, from the initial state to final state. And these changes, since they are done very infinitesimal amounts, these can be reversed also. Okay, this can be reversed very easily by a small adjustment of the variables. Okay. So if you just make a small adjustment of the variable, you can actually reverse the changes. That is why it is called the reversible process or reversible expansion. Okay. So you can do that also. That means this is done in a very successive stages of infinitesimal amount. Changes can be reversed because amount is very small change. So what will be the work now? So in this case, what happens? Suppose you change the pressure by a small amount PEX, and then the gas inside the gas has a pressure of itself, kinetic pressure of the gas. So if you reduce if you make the pressure now, what becomes when the piston will come at equilibrium, when the external pressure is same as the internal pressure. Okay. So therefore, this external pressure will become now P minus dP. P is the internal pressure reduced by a very small amount. Okay. So every time PEX, external pressure, has to be made equal to this P minus dP. Clear? So therefore, this PEX we are replacing by P minus dP. Okay, because we are studying in this particular case expansion, so pressure is decreasing. We are decreasing the pressure by small amount. So now you see that we have removed external pressure by the pressure of the gas, internal pressure of the gas. What is the advantage? Because it's internal pressure of the gas, so now we can bring in the equation of state. We can bring in the equation of state into the work expression. Okay, so that is why we did that. Now we can separate this out into these two form integration. Now this part we neglect because both dP and dV are very, very small. So therefore their product is much, much smaller. So we can simply ignore this. So and say that work done is simply the integration of this expression. Between, you are doing integration between the lower limit, that is the initial volume, to the final volume. Okay. Now if you consider the isothermal expansion, we are considering isothermal expansion of ideal gas now. This is the general expression. Remember, this is the general expression. Now, whatever gas is given to you, suppose in the test I give you another equation of state for ideal gas PV equal to nRT. Suppose I change it and give it to some other gas, some other equation of state. I say that okay, this is the gas which follows this equation of state, and I give you a different equation of state. From that equation of state, you have to find out this pressure in terms of volume, and then substitute it here and integrate. That is the only thing. Okay, you may get a different expression for what. Okay. Now in this case, what is P? I substitute this P from here, so P equal to nRT by V. So if I do nRT by V, nRT constant comes out because it's an isothermal process, temperature is constant. So you have 1 by V dV integration, which is nothing but log of V2 by V1. So log of final volume by initial volume. Okay. So this is your isothermal reversible expansion work for any ideal gas. W equal to minus nRT log ln, log base E actually, log of value, final volume by initial volume. Okay. Now this is from here, you can see, say for example, now expansion work. V2 with expansion means final volume is greater than initial volume. Here, final volume is greater than initial volume. If final volume is greater than initial volume, then this logarithmic torque will be positive. So therefore, work will be negative. Okay. So W will be less than 0. That is negative. This negative means only thing is the sign convention. Similarly, you have say compression. If you have a compression work, so then V2 is less than V1. Okay. So if V2 is less than V1, then this logarithmic torque will become negative. Okay. So the overall work becomes positive. So W will become greater than 0 if you are doing a compression. So this is basically a sign convention. Clear? So if you find, say, for example, W is equal to minus 100, say, kilojoule per mole or something, minus 100 kilojoule. That means that only thing is that actually work is 100 kilojoule and minus sign means it was an expansion work. Okay. Or if you see that W is equal to 100 kilojoule plus 100 kilojoule, that means that work is 100, but it, since the positive sign means it was a compression work. So it is simply a sign convention. Clear? So you should understand this because this is the convention that we will follow. Okay. And this is coming from the fact that we have taken the displacement to be against the opposite force, against the force. Therefore, this negative sign is coming for expansion. Okay. Now we'll try to compare what happens in expansion compression if we perform the work in a irreversible, reversible both ways. See, we can do it in both ways, right? We can go from initial volume V1 to final volume V2, either reversible way. Then I get this is the work done, okay? Or same change we can make it in an irreversible way also, just directly changing the pressure to the final pressure. In that case, work is this, okay? Then we should compare, okay, in the both process. What is happening? We are making the same changes, same initial state to same final state, but we are doing a reversibly and irreversibly. We are getting two different work, two different expressions. Okay, how do they compare? Okay, so that is what is important to know. It is easy to understand that in this from this figure. Say suppose this is just a pressure versus volume plot. Pressure versus volume plot, and you know that pressure versus volume plot is like this. It's a rectangular hyperbola type of an expression, say for ideal gas. Okay, this varies. Now let us take 2 points, point 1 to point 2. This is first point is one state, P1, and point 2, this is state 2, is pressure volume is P2. Okay. Now suppose system you are expanding from state 1 to state 2. State 1 volume is less, state 2 is volume is high, so it's an expansion process. Now in first process what we are doing, we are directly changing to the final pressure. That means it's an irreversible process. I'm directly changing pressure to the final pressure, P2, and then system is expanding against that constant pressure. Okay, so I directly change it to final pressure that I want, and then allow the system to expand. So that's an irreversible expansion. What is the work done? You have seen work done is final pressure into delta V. Okay, so final pressure P2 into delta VT. So this shaded region, this is the work done. Okay, this is the work done, irreversible process work done. Now suppose now I have decided that I will carry out the process in 2 steps. I create an intermediate step, say 1 prime, with some pressure volume values. Okay, so what happened? What I am doing now? Pressure P1, I directly change to some intermediate pressure P prime. Okay, and then see what happens to the system. Then second time, this P prime 2, I again reduce the pressure to P2. Okay. So basically, this irreversible process I have made into 2 irreversible processes now. Both are irreversible processes because I am directly changing the pressure to the final pressure. So the first step, what will be the work done? In the first step, final pressure is P prime and volume change from say V1 to V prime. So this region, this small rectangle region, this is the work done. Now next time I am going from P prime to P2. This is the final pressure and volume is going from V prime to V2. Okay. So now this portion, if you see this portion is the work done of the second step. So what is the total work done? Total work done is simply sum of these two. So now you see I am getting this portion as the work. Okay, like this. So this is slightly more than this one. Clear? Now I increase the number of steps between initial and the final. Suppose a very large number of steps, so that I incrementally change. I make the change in pressure very infinitesimally small, and then see the expansion of the process, and then carry it out. If I do that for a very large number of steps, then I will get a continuous, this entire car will be covered. Okay, so the work done will be this entire area. And that corresponds to what reversible process means. If we carry out a process, a very large number of steps, each step we are making an infinitesimal small change, then that is a reversible process. So now once I reach 1 to state 2 in this manner, this is nothing but I carried out the process in a reversible manner. So therefore I am getting this work, whole work I am getting. Okay. Now if you compare, what do you see? You see that I am going from the same state 1 to state 2. Here also, but the work that is done by the system here is much more than the work done by the irreversible process. Okay, so this shows that your reversible work done is always greater than the irreversible work done. Okay, so if you want to get maximum work done from a system, then you must carry out the process in a reversible manner. This shows that. Okay, it's a very important observation. Reversibly carried out work is always greater than the irreversibly carried out work. Okay. Now another thing you see, suppose we are now doing the reverse thing. We are compressing the system back to the initial state. Okay. So now this is my state 1 and I'm trying to go back to this 2. So I have reversed now, doing a compression. When you do a compression, then you have to perform work on the system. Okay. When you expand the system, then system actually does the work. Now, if I do that again, if I do the compression in one single step, irreversible way, then directly I am changing pressure, increasing the pressure from P1 to P2, and then compression happens. So what will be the work done? Final pressure into change in volume. So this whole area is the work that has to be done on the system. Clear? Irreversible process. Now exactly in a similar manner, suppose the compression I do it in 2 different steps. Both are irreversible. First, pressure changing to P prime. So the work done will be P prime into 2 volumes. So this is the work done. P prime into this volume change. Then P prime to P2 I am going. So final pressure into this volume. This is the volume. So this whole thing is the area now. Okay. Area, whole area is the work. So what is the work? This plus this. So this much work is now needed. Okay. See, this work is less than this. Okay. Now you do a reversible. Same compression process. I do a very, very large number of steps. Each step with infinitesimally small change in volume. Small reduction in volume. So what happens now? Your work that is to be done is basically the curve, the entire area under this curve. Okay. So this is irreversible. This is reversible. Now what you see, suppose you compare between reversible processes. This is reversible expansion, this is reversible compression. Now in the expansion process, this is the work that is done by the system. Work done by the system into the surroundings. Okay. And this is the work done by the surrounding on the system to compress it back to the initial state. Okay. So in both the cases, these two works are same. If you are carrying out the process in a reversible manner, then these two works are same. You can see the area under the curve is same. So the work obtained in the surrounding is same as that required to compress the gas back to its initial state if the processes are carried out in a reversible manner. Now look at the irreversible process. Now here, this is the work. We obtain only this much of work in the surrounding from the system. Whereas to compress it back, we need to do so much of work on the system. So this is much larger than this work done. Okay, that means work that one is getting in the surrounding here is less. See, I have written it here, is less than the work required to compress the gas back to the initial state. So compressing the gas back to the initial state required this much of work. Whereas system while expanding gave me only this much of work. Okay, so this is more. Okay, so now 2 things are very important here, and which will be very, very important. One is that going from one state to another state, if you want to get maximum work, you must carry out the processes in a reversible manner. That is one way. Okay, and if you carry out that process in an irreversible manner, then your cost, that means the energy supplied that has to be supplied by you to bring the system back to the initial state, is much higher than the energy system is giving you. Okay, so if you get 10 kilocalorie energy here, then you may have to supply 50 kilocalorie to bring the system back to the initial state. Okay, whereas here it is exactly the same work in reversible case. Okay, so these two are very important points between reversible and irreversible process and the work that you get from the two. Okay, so I hope this is clear to you. Now, let us bring about another thermodynamic variable now, enthalpy. We will get back to enthalpy definition. But first, why this enthalpy? Why do you need enthalpy? Okay, suppose so far we define only internal energy, U. Okay, why we need another variable? See, more and more functions, more and more variable comes into the picture, means more and more life becomes complicated. Okay. Next, we will see that entropy comes into the picture. Then Gibbs energy, Helmholtz energy, those also we will bring in. So why we are bringing one after another new variables or new functions? Okay, is it just to kind of for fun, or are they really required? Okay, they all have some significance. Okay, they have some very important contribution, very important significance. That's why we are bringing different functions. And when you bring a new function, means the previously defined functions are unable to do something. They may have certain restrictions, okay, or certain limitations. They could say something, but they could not say something about the system. That is why we are bringing in another function. Okay, so that's the reason. It is not just like that functions are brought in, different thermodynamic functions. Okay, now first we'll see why enthalpy is so important. Suppose our starting point will be always first law. Okay, this we know. First law is our starting point. So the change in internal energy is equal to dq plus dw, change in thermal energy and the work done. Okay. Now, if we assume that only mechanical work, that means system is doing only expansion compression, no other additional work. Okay, additional work means non-mechanical work. Okay, say electrical work, magnetic work. Those are all different chemical work. Those are all non-mechanical work. They are known as the additional work. We are assuming now, for simplicity, that only work is mechanical. That means this piston is going up or down like that, expansion and compression happening for the cylinder. If you do that, so we can write down like this first law. Now, suppose that you are carrying out the change at constant volume, isochoric process. Change happening at constant volume. That means you are not changing the volume of the system, but you are following something processes or doing some changes in the system. Since volume is not changing, then this term will disappear. So what will be the change in internal energy? Will be same as change in dq at constant volume V, or you can see that equal to qv. Okay. So this is an important point. What it says that if you keep the volume constant, then the amount of heat or the energy that you are supplying to the system or getting from the system, okay, that is same as the change in the internal energy of the system. So you found one equality here. Change in internal energy is the same as the change in heat or thermal energy at constant volume. Okay. Now, if the heat is supplied to the system, then QV is greater than 0, and if a system releases heat, then Q is less than 0. So this way we get to know how delta U can be measured. So if we can perform an experiment where system is at constant volume, that means there is no change in volume, and then you are carrying out a process, there is some heat exchange happening with the surrounding. If you can measure that heat exchange, say there are some methods, say some calorimetric method or something where you can measure the heat exchange or the energy change for a process. Suppose you can measure that will be the same as your internal energy change. So therefore, this is a way to measure internal energy. Clear? So if processes are done at constant volume, then it's good. Internal energy is sufficient. It can be made equal to the energy exchange that is happening. But now suppose assume that your process is not happening at constant pressure. Okay. In fact, most of the processes you will see that they are volume is not kept constant, rather they happen at constant pressure. But you cannot simultaneously keep pressure and volume constant. If pressure is constant, volume has to vary. Okay, because you are keeping the pressure constant. So therefore, if the pressure tends to increase, then volume has to expand. Okay. Or your pressure tends to decrease, then your volume must reduce to keep the pressure constant again. Clear? So therefore, if pressure is constant, then volume must be allowed to vary. Okay. And if volume is allowed to keep constant, then you have no control over pressure. Now pressure can either increase or decrease. That is a possibility. So if suppose constant volume, everything is fine. Now suppose if you carrying out a process at constant pressure, then system will change its volume, we know. So if the system changes its volume, then what will happen? That means system changing volume means it is doing some mechanical work. It is doing some compression expansion work. Okay. So whatever amount of heat you will supply to the system, some part of it will be utilized for that expansion compression work, that mechanical work. So some part of the energy that will be supplied will be wasted in that process. Okay. So therefore what will happen? This change in du or change in internal energy will be less than the heat supplied. Because if you have supplied, suppose you supplied 10 kilojoule of heat, out of that 2 has been utilized by the system to expand and compression, then what is the remaining will go to the internal energy will be 8. Okay. So your internal energy change will be less than the energy supplied or energy obtained from the system. Clear? So if it is a constant pressure process, then whatever energy you are supplying, part of it will be utilized for the expansion compression process. Okay. So therefore, now du cannot be written equal to dq. It should be less than dq. Okay. In other words, if you carry out a process at constant pressure, now you cannot measure the heat exchange and say that this is my change in internal energy. You cannot say that because it is not equality, it is an inequality now. It's less than. Okay. So if you measure, say the energy exchange is 100 kilojoule, then only thing you can say that internal energy change will be less than 100, but you cannot measure it exactly. This is the drawback of internal energy, or not drawback, it's basically a limitation of internal energy. It cannot explain processes at constant pressure properly. Okay. So for that we are defining, that is why to avoid that or to get rid of this limitation, we are defining another thermodynamic property of the system or thermodynamic function, which is known as the enthalpy. Okay. So enthalpy is another thermodynamic function, that is why we are bringing it here. Okay. It is useful for processes at constant pressure. And we are defining it H is equal to U plus PV. This is by definition. By definition, enthalpy is actually equal to internal energy plus pressure and volume product. So pressure volume product is basically work, that is the energy dimension. So dimensionally they are all energy. Okay. Now we have already discussed U is what state function. Pressure and volume, they are also state variables. They define a state. So therefore H is the sum of the two. So H also must be a state function. Okay. So enthalpy is also a state function. So if enthalpy is a state function, then all the properties of state function will be satisfied by H. Okay. What are those properties? We discussed that. So the change of H from one state to another state will also become independent of path. Okay. So it will be a path independent function. It only depends on the state. Then its variable dH, differential, will be an exact one. Okay. Differential will be an exact one. That means you can write it down in terms of partial derivatives the way we defined. Okay. So H essentially will have same characteristic. It's also an extensive property, same characteristic as U. Okay. And this definition is this. And why H is required? Because internal energy cannot be properly used to explain processes happening at constant pressure. Okay. Now we will see how H can help there in enthalpy at constant pressure processes. To study constant pressure processes, how H can help. Let us see that. Okay. Now H by definition, so the complete change you can write it down like that. Suppose for a process there is a change in internal enthalpy, so dH is equal to du plus PdV plus VdP. Okay. Now from first law we know, first law change in internal energy is actually dQ plus dW. Okay. Heat exchange plus the work done by the system plus PdV plus VdP like that. Now we assume that this process is done at constant pressure. So if that's the constant pressure, then VdP this term becomes 0. So we have complete change in enthalpy is equal to dQp now at constant pressure plus dW plus PdV. Okay. Now we are making further approximation saying that let us assume that system is doing only mechanical work. Okay, system is only doing mechanical work. That means expansion compression work. No additional work is there. So in that case, what will become dW? dW will become minus PdV. Okay, so therefore these two terms will cancel each other. Okay, these two terms will cancel each other. So therefore dH equal to dQp. So now you see, you found a way to measure enthalpy change. If you have a process carrying out a constant pressure, and if you can measure the corresponding heat exchange, heat absorbed or heat released at constant pressure, that will be same as the enthalpy change for the system. Okay. Now knowing enthalpy change for the system, then you can apply the equation of a definition of enthalpy and all. Then of course you can find out what will be the internal energy change. Okay, in that way you can find out. So directly measuring the heat exchange at constant pressure, you cannot get the internal energy change. Okay, so that is why we brought this enthalpy concept, because enthalpy change is same as the heat exchange at constant pressure. Okay, so that is what is important consequences of enthalpy. Okay, let us quickly follow this then. Okay, let us now define what is this, heat capacities. Okay, heat capacities, what is the heat capacities? It is the amount of heat that is required to increase the temperature of 1 mole of a substance. Okay, that is a simple definition of heat capacity. Okay, specific heat, it is the change in 1 gram of a substance. Okay, now here we are taking 1 mole, so we call it a heat capacity. Now heat capacity can depend on how you are carrying out the process, depending on the volume and pressure, particularly for gas, because the amount of heat required if you perform the process at constant volume and that required at constant pressure, they need not be the same. Okay, because that depends on the how you carry out the process. That means the path, the Q. Okay, so therefore two different scales are often defined. One is the specific heat at constant volume, and one is the specific heat at constant pressure. Okay, so CV, constant heat at constant volume, will be simply dQV at dt. So the amount of heat required to raise the temperature of 1 mole of a substance, okay, at constant volume, and this will be the amount of heat required at constant pressure, okay, by 1 mole of a substance. This is the Cp. Okay. Now from here, we already knew, remember previous page, we saw that your du equal to dQv. So your heat exchange at constant volume can be equated with internal energy change. Okay. So therefore, this dQv can be replaced by du, change in internal energy. Okay. So Cv equal to what? We can write it down like that, del u del t at constant. Okay. Remember, since we are transforming into u, immediately you have to write partial derivatives. because u is a function of many variables. So therefore you have to use the what? Use that partial derivative concept here. So Cv can be written as del u del t at constant v. Okay. That shows that if you can measure internal energy at a function of temperature, and if you plot, then whatever graph you find, its slope will give you the Cv. Okay. So the Cv specific heat at constant volume is nothing but the slope of the curve between internal energy and temperature. Okay. So du equal to this dqv, that means Cv equal to, can be written like that, or you can write it down in different way, du equal to Cv dt, or if you have n mole, then n into Cv into dt, because it's an extensive property. For 1 mole it is Cv dt, therefore n number of mole will be n Cv dt. And if you want to, if you are making a change from one particular temperature to another particular temperature, then you have to simply integrate this and you get the total change in internal energy. So this is a way to calculate internal energy also, provided you know the specific heat and if you know the temperature range. Okay. So from there you can find out this. So this equation is quite important equation. Similarly, we have just now we have seen that your age change in enthalpy is equal to dqp. Okay, amount of heat required at constant pressure. So dH equal to dqp. Now what is dqp? Dqp we have defined as the change in enthalpy. Okay, so therefore again we can write down the Cp equal to dqp dt. Dqp is actually dH, so therefore it becomes del H del T at constant. Okay, very simple. Okay, because dH equal to dqp, so therefore we simply write del H del T at constant P. That is actually equal to Cp, specific heat at constant. Sorry, this molar heat capacity at constant pressure. Okay, again from here you can write for n number of mole, dH can be written as n Cp dt, and if you are given two different temperatures, then you can simply integrate this out. So these are the equations most commonly used in different type of numerical problems. Now, often the Cp and Cv, they are independent of temperature, but they can depend on temperature too. Okay, they can depend on temperature too, so they can vary with temperature, and generally, if suppose they can follow some kind of equation like this: a plus bt plus c by t square, and so on. It can be a function like this. If that is the situation, then you simply, this is the definition. So you write down the Cp expression and you simply integrate it. Okay, all the t's values are given, then apply the formula of integrations of the respectively, and then you can find out the value of delta H. Okay. You can simply find out the value of delta H. So these two are very important relations between between heat capacities and the internal energy change and the enthalpy change of the for the system. Okay. So this is what we defined. So what we defined, we talked about the internal energy. Okay, and shown that internal energy change is same as that of the heat exchange at constant volume. So constant volume problems are all right, but at constant pressure we cannot write it like that, because now internal energy change will be less than the heat exchange, because some part of the heat is utilized by the system, rest is available. Okay, so therefore we bring in the another function, thermodynamic function, which is the enthalpy. Okay, so we did that, and then by doing that we showed that now heat exchange at constant pressure is nothing but equal to the enthalpy change. Okay. And from there we can also found out that importance of delta U and delta H, they can also be found from this variation of specific heats or the heat capacity of the systems. If we know the heat capacity of the system, then we can find out, is another way to find out the change in internal energy or enthalpy of the system. Okay. Now, depending on what is the expression of Cp with temperature, you have to apply the appropriately that. Okay. Now let us move further a little bit and see how this U and H, these two functions like internal energy and enthalpy, they vary with different variables, or they change with different system variables. Okay. If you change volume, if you change temperature, or if you change pressure, how these values change. It is important to try to study that. So when we try to see, first thing we write is U as a function of volume and temperature. Okay. We are writing as a function of volume and temperature. We can write it down any two of the three parameters, pressure, volume, and temperature. So we write it down like that. Now, once U is a function of these, then total change in internal energy for a process can be written like that. So du, del U del T at constant V dt plus del U del V at constant T. Okay. So we can write it down like this. Now, first thing what we are trying to see is with respect to temperature at constant volume. So we're trying to see how U changes with temperature at constant volume. Now, if you do constant volume, this term gets disappears. dV equal to 0. So this term disappears. So du that we change in internal energy at constant volume is nothing but this del U del T at constant V dt. Okay. So at constant volume, this is the expression. Now del U del T at constant V, what is that? That was actually Cv. Just now we discussed del U del T at constant V equal to Cv. Okay. So therefore, delta U will be equal to simply Cv into delta T. Clear? So this part is Cv. So therefore, delta du equal to Cv dt or delta U equal to Cv delta T. Okay. So we can very simply do the measurements. Now, with respect to volume, what happens to the value of U with respect to volume? Okay, del U del V at constant T dV. We want to find out what happens to U at with respect to volume at a constant temperature. So temperature is now constant. If the temperature is constant, then this term disappears. Okay. So we remain with this term. Okay. So this is the term. So therefore, to know this, we must know what will be this term with temperature. So how internal energy changes with volume? How internal energy changes with volume? This has to be first determined. Okay. So this is basically determined by what is known as the Joule experiment. So what I will do, I will stop here and then try to see whether this one will discuss in the next class, whether you have understood or whether you have any doubt. Okay. That I will you can now try to explain. Let me come out of this then.